Yes. But today we concentrate on Brownian motion. So no antigrade study. Okay? By the way, I'm sorry I did not bring any chocolate.
Next time.
Or sweets. Hope you that we have got enough chocolate in the morning. Okay. So let's continue our investigation of self-intersection local times. And here I will recall first the result that we discussed in the second lecture about double intersection local time for the Brownian motion. We said that it only exists if the dimension is less or equal than 3. Okay? It exists as density for the occupation measure. Okay? So this occupation measure has a density, and this density is even square integrable, and it is even continuous in the RG, okay? But not at the point 0. And we have seen that it blows up around 0. Its limit is infinite. And according to the dimension 2 or 3, we have even seen the scale of how much it, in what scale it tends to plus infinity. In dimension 2, it tends to plus infinity in the logarithmic scale. If you remember, it is logarithm of 1 over the norm of u. And in dimension 3, it is a little bit more complicated, okay, with some different expression. Okay. So, we will concentrate on this dimension 2 and 3. Okay, we still have the self-intersection local time, and we still want to do some description of this self-intersection local time before moving to higher dimension, where we will see the appearance of generalized self-intersection local time. Okay, so the title is okay. This is generalized self-intersection local time, but I will begin by no, let's say normal or usual self-intersection local time. Then I will move as a second part to the generalized self-intersection local time. So in dimension 2 and 3, so we have this following result that gives us a representation given by the E to Wiener expansion, the chaos expansion that I presented yesterday. So the E to Wiener expansion is given by the following series. Okay. So here you may ask, where are the multiple E2 stochastic integrals? Of course, each of these Hermite polynomials here with the increments of the Brownian motion, of course. B is the Brownian motion, it is a d-dimensional Brownian motion, so it is B1 of t, the coordinates, okay? BD of t, okay? So BG is one of the coordinates, okay? Okay, so each of these expression here, as if you remember this formula that I showed yesterday, it expresses this Hermite polynomial as a multiple E2 integrals, okay? So the multiple stochastic integrals appear here in this part. Okay. So what we are going to do, this result was proved in 1995, and our aim is to just make some estimates for each term of this E to Wiener expansion. Okay. So we try to find some almost sure bounds for these integrals here. Okay? Just to understand in a most sure way how these terms of the E to Wiener expansion behave. Okay? So I remind you that rho 2 of u, we are in dimension 2 or 3. Okay? So it tends to plus infinity. when u tends to 0. Okay? We want to understand this in the convergence here is in L2 and possibly also in Mostrel, if you just review the results that I showed yesterday. Okay? So we want to understand this, but from the terms of the E2 expansion. Okay? So we have another representation for the second intersection of time, and we want to understand this, but just from these integrals. Okay? Okay. So we'll do some estimates. Okay? Some estimates related to these integrals. Okay. So we begin by the following proposition, where we look to integrals of a delta 2 of this Gaussian density here, pt minus s d, and we multiply it by 1 divided by t minus s to the power I. So we want to understand the behavior of this Gaussian density when integrated with, when multiplied by this term here, and be careful, we integrate with respect to s and t, not with respect to u. Okay? I remind that p epsilon d x or q is divided by 2 epsilon, and here we have 2 pi epsilon power the density of the normal with the epsilon, the identity. Okay? Okay. If we integrate this with respect to x, and Rd, of course, it gives us 1, but we want to integrate with respect to this parameter, t minus s. So, okay? And then we want to see how this whole integral behaves when u tends to 0. Okay? We will see later why we want this type of integral. Okay? Why we started by estimating this type of integrals. Okay. So the result here is not such difficult because you can make a change of variables here. You see that the integral only depends on t minus s. Okay. So we can make a change of variable like s1 equal to s, and for example s2 is equal to t minus s. If you remember the integrals that we treated before over delta 2, we have used such kind of change of variables. So we can change this integral, and a gamma function will appear. It's not such difficult a task to obtain this equivalent expression. So if alpha is greater than 1 minus d over 2, we will find that this integral is equivalent when u tends to 0 to some constant here. This is gamma function divided by the norm of u to this power. And if alpha is equal to 1 minus d over 2, we will find the logarithmic term here. Okay? Okay. And remark that we see that this integral blows up. So since we have this equivalent expression, it is clear that when u tends to 0, this integral tends to plus infinity. It is like the behavior of root of u, and even it will appear in the description of root. Okay. Okay, next estimate will be related to Hermite polynomial with Brownian motion. Okay, so if we consider one-dimensional Brownian motion, then most surely we have the following inequality. Right? Of course, just a minute. If I go back, why we want these kind of estimates? Because they clearly appear here. Okay, we have Hermite polynomial from increments of one-dimensional Brownian motion divided by square root of the distance. Okay, we want to get some estimate for this. Okay, and we have an estimate which is, be careful, it is almost sure. It is almost surely. It is not an L2 or in any other sense, it is an almost true estimate. So what we find is this factor here and divided by t minus s to the power n divided by 2, and here we have an exponential part with the absolute value of wt minus w of s. Okay. It's a new estimate that we obtained, and I even prepared the proof for it. Okay. Also, another remark before even seeing the proof: this inequality does not depend on S and T. So S and T are fixed. Okay, so it holds for any S and T.
But T bigger than S.
Of course, of course. So for the proof, okay, first. N polynomial from Wt minus Ws divided by the square root of T minus S can appear in, we know the generated function of N polynomial. I think I showed this yesterday. It is the function exponent Tx minus T squared over 2. If you make a Taylor series of this function with respect to T, and then you make Tn, what you find here is N polynomial. Okay? So this is generated function of N polynomial. The expression here, so I just need to rescale it, okay? It becomes exactly like the generator function, and we will find this series expansion given here. And this holds for any complex number Z. From this point, we see that this value here can be obtained as the nth derivative of this function from Z. Okay? So this expression is nothing else than but the nth derivative of this function, of course, at the point Z equal to 0. Okay, but now this expression here, exponent of Z times Wt minus Ws minus D squared divided by 2T minus S is obviously an holomorphic function. Okay, it's an holomorphic function on the entire set C. Okay, there's no problem. It is holomorphic. And so we can apply, to obtain the nth derivative at the point 0, we can apply Cauchy formula. Applying Cauchy formula, for example, we can choose, since we want to obtain the derivative at the point 0, we can choose this contour as a unit circle. Okay, so we are looking for the derivative here, and the function is holomorphic in the entire C. So we can choose as this contour the unit circle, and it is enough to integrate this holomorphic function divided by Z minus 0 to the power n plus 1, and here are some concept that should be used. Okay, Cauchy formula. Okay, but then using Cauchy formula, we can do some estimates. Okay, we can do some estimates. Since we integrate over complex numbers of modulus 1, okay, we can do some estimate here. This denominator here will disappear, of course, and for the this exponent part, we can check that for any complex number of modulus 1, we have the following inequality. Okay, it's not hard. Okay, this is simple exercise with the exponent of Z times something minus Z squared divided by 2 times something, and you have the modulus is equal to 1, so you can find the maximum, let's say, of this this function. Okay, it's not hard to find this upper bound. And so we obtain the inequality. Of course, you take here modulus, okay, and modulus of this integral will be less or equal than the integral of the modulus, and so on, and you obtain the inequality. is interesting. I mean, it's a new inequality, a new estimate, and it is true almost true. Okay. Another one in the same context, there is another inequality that it is always used with Hermite polynomial. Old inequality that can be found in the book of Zebo about orthogonal polynomials. Okay? And it is useful in studying self-intersection over time. So, if alpha, we fix alpha first in the interval 1/4, 1/2, okay? Then there is a constant C, positive constant C, such that for any integer n and any real number x. Okay? So the same constant for each x and each n. Okay? This inequality here is uniform in x, uniform in n. Okay. So Hermite polynomial multiplied by exponent of minus alpha x squared is less or equal than this factor here related to n. Okay. You can ask why we do need this estimate. Okay, again, we can come back to the itogenal expansion we started with, and we will see that we need such kind of estimate. Okay, so let me just go back a little bit here. So here you have Hermite polynomial, and what's this pt minus sd? Of course, we have this expression. If we just take t minus s, we'll have t minus s. Minus s. Okay, and this will be a product of exponent of minus exponent minus xe to xj squared divided by 2 t minus s. Exactly, if you make this product here, you will have an appearance of there is a product of this Hermite polynomial here, and usually divided by the square root t minus s. And here there is exponent of minus reduced square like this divided by 2t minus s and square root of 2 pi. Okay, so if you write this as a product, of course, then you will have exponent minus uj squared divided by 2t minus s with each sum of these terms. You know? I mean that this whole expression will be exactly a product of this kind of expression. Okay, each Hermite polynomial will have one single term from this product. Okay, so we can obtain an estimate. Okay, now it remains to combine these estimates, and we can obtain the following result. Okay, so almost surely here we denote by zi the maximum of the BIS of the interval 1. So if we take the absolute value of these sums of integrals here, okay, that appear in the itogenal expansion of the self-intersection over time, so what we obtain as an inequality, we will have some constant multiplied by the logarithm factor. This only happens in d equal to and k equal to 0. In the first element of the itogenal expansion, and this only in dimension 2. In dimension 2 or 3, or in dimension 3, we already said this upper bound here with some norm, the norm of u to the power k plus e times 2. What is k? K is, you have here n1 plus nt is equal to 2k. This is almost sure bound, obtained by combining the previous estimates, and it at least there is the appearance of the logarithmic part, which appears also in the behavior of the self-intersection local time in planar case around the origin. And also there are some negative powers of the norm of u, and we remember that in three-dimensional case there is this the appearance of 1 over the norm of u and the behavior of the self-intersection local time around z. So that was our result concerning dimension 2 and 3. It's an almost sure upper bound, just we try to understand how these elements from the equivalent expansion behave when u tends to 0. Okay? Okay. Now we'll move to higher dimension. Okay? Dimension d greater or equal than 4. As we said before, the self-intersection of the time does not exist here. Okay? However, we can replace it by something. Okay? So here is a really a good point in this theory. So we consider the d-dimensional Brownian motion in dimension greater or equal than 4. Of course, this limit does not exist in L2, and the related occupation measure also does not have a density. We have seen this. However, this limit we can find it in some bigger space. Okay? It exists in every sovereign space D2 gamma with index gamma smaller than 4 minus d over 2. I will explain what are these spaces. Okay? So this is the generalized double intersection local time. Okay? So we have something that does not exist as a limit in L2 as the density of occupation measure. However, we still can define it, but in some space, a new space, which is bigger than the usual LP spaces. Okay? The limit is not a usual random variable. It is a generalized random variable. Okay. We'll see what does it mean, this space D2 sovereign space. Okay, here I will try to explain the construction of these spaces. So again, we have the d-dimensional Brownian motion. The space D2 alpha is the completion of the formal space. So we take elements from L2 space, or square integrable random variable, measurable with respect to the Brownian motion. Of course, we said yesterday that each such random variable has a Naoufel expansion, a chaotic expansion, but we will take only those who have finite terms in their Naoufel expansion, polynomials, like polynomials. Okay? And then we take all these random variables and we make the completion. Okay? With respect to a new norm. Okay? Respect to the new norm, this new norm with indices 2 alpha is the sum from 0 to n k plus 1 to the power alpha, and here expectation of ek of fk to the power 2. Of course, ek of fk is a multiple e2 integral. Just this is a notation. Okay. So let's just see a little bit. So eta. It's important to understand this. So if we take eta sum from 0 to n ek fk. So this is square integrable random variable, measurable with respect to the Brownian motion, but having a finite number of. If we take its L2 norm, okay, or it is the same as the second moment. So what it is, since this is these terms are orthogonal in L2, okay. So this is the sum. It is like an orthogonal base, okay. So the sum from 0 to big N of the square norm of this. Okay? Okay? It's like you have some vector in some written in some orthogonal basis, so its square norm will be the sum, okay, of the square norms of the types. Okay, but now we will not take the completion with respect to this norm 2. We will define a new norm. We will modify this norm. Okay, we will multiply here by something. So this new norm 2 alpha will be the sum from 0 to n, and here k plus alpha, k plus 1 to the power of alpha, and we will take expectation of ek. Okay? So we modify the usual L2 norm by multiplying each term by k plus 1 to the power alpha. Of course, okay. So this defines, this is a well-defined norm in the set of all random variables of the following form. But if we take the completion, what we really get at the end? Okay? What we really get is the following. We will find, okay, so d2 alpha, what will it will obtain? It will obtain some elements. Okay, these are not elements from L2 and so. Okay, these are not elements from L2, but okay, I will denote this like this. All this possible series, okay, all the possible sums like this, okay. So I will denote sum from 0 to infinity. It may stop at any level, okay. Ek of A. But it does not converge in L2, it converges in this sense. Okay? Such that the series of the power alpha is finite. So we consider all the formal series. This is maybe the right way. It is like a formal series of multiple integrals. This is not a square integrable random variable, because this series does not converge in L2. It converges with respect to this side. Of course, it is, if alpha is equal to 0, of course these are usual random variables. Okay? But if alpha, for example, is equal to 1 or minus 1 or something else, this is a new norm, and mainly if alpha is negative. If alpha is negative, this cannot converge in L2. Okay? So, what is D2 alpha? It is the set of all such series, okay, that converge with this, with respect to this norm. Okay. If alpha is positive, okay? If alpha is positive, okay. If alpha is positive, then what do you find? You find a space which is included in, of course, you may just make a small, you can understand it. Suppose that alpha is, because alpha here is fixed, okay? Suppose that alpha is strictly greater than 0, of course, and that this series converge. Of course, then we can deduce easily that this series converge, right? Because k plus 1 to the power alpha is always greater than 1, okay? So for positive alpha, if this series converge, then without this term, this series also converge. It means that for positive alpha, this space is included in L2 space. Okay? That's here exactly for alpha positive, we have D2 alpha is included in D20. D20 exactly coincides with the usual L2 space. But the problem is when this alpha here is negative. Okay? If this alpha is negative, it means that we have to divide this series by something to obtain a convergent series. You understand? If alpha is negative, for example, -1, it means that the series of these square normals divided by k plus 1 is finite. So possibly the series without k plus 1 may not converge, okay? So you have to divide it to obtain something convergent. Okay? So for negative alpha, this space D2 minus alpha, yes, D2 minus alpha is always bigger than the space A. It contains strictly the space A. So that's why we say that elements here are generalized invariable. Okay? This is bigger space than usual L2 space. Okay. Here we define there is this property that if you take D2 alpha and D2 minus alpha, they are one is the dual space of the other. Okay, and we can define, since they are, you see here, if alpha is smaller than beta, then D2 beta is included in D2 alpha. So it means that if alpha becomes bigger, the space D2 alpha becomes smaller. And we can define this intersection here of all these D2 alpha for positive alpha. It will be the smallest one that can be obtained. Okay? For the union of the D2 minus alpha, because you see here D2 minus alpha, D2 minus, it becomes bigger and bigger, so their union will be denoted by D2 minus infinity. It is the space of all generalized functions. Okay. So here, the self-intersection local time, which does not exist, but it may have a sense, but in a generalized sense. Okay. It exists in some Sobolev space with gamma smaller than 4 minus d over 2. Of course, now we have the condition that d is greater or equal than 4. Then, of course, 4 minus d over 2 is clearly negative. And we have gamma is strictly small. It means that the self-intersection of the time only lives in some Sobolev space with a negative index. So it is a generalized invariant. Moreover, even we have the e-to-Wiener expansion of this generalized Wiener function. Okay, it also has an e-to-Wiener expansion. Of course, any generalized, by definition, it can be written like this. Okay, so the e-to-Wiener expansion of this row 2 of u, even in this dimension greater or equal than 4, is the same as before. Okay, so just this one. The same e-to-Wiener expansion, but now, of course, this does not converge in L2 sense. It converges with respect to distance. You have to divide each term by k plus 1 to some power in order to obtain a convergent series in L2. Okay? Okay. So now we want to concentrate on this case when the dimension is greater or equal than 4 and that we deal with something generalized, not usual random value. For this, we will begin by using the following theorem. Okay. So we consider the classical Wiener space. What is the classical Wiener space? it is the space of all continuous functions from 0, 1 to Rg, which branch at a point 0. You can imagine the space as all the possible trajectory of the Brownian motion. And mu is the standard Wiener measure. It is the measure defined on this space such that you can define a Wiener process easily on this space. Okay. Now what do we want? If a generalized Wiener function, if we have a generalized Wiener function which is positive in the following sense, okay? You remember that I said that these spaces are like the dual of each other. D2 minus alpha is the dual of D2 alpha. So that if we take an element here and an element here, we can make a canonical bilinear form. Okay, there is a dual relation. Okay, so whenever we test some generalized function by a test function, we find a positive result. We say that the generalized function is positive. In such case, this generalized positive function can be represented by a finite, unique, finite positive measure on the Wiener space. Okay, in the following sense. So that this canonical bilinear form here will be written as an integral of a Wiener space. Okay. Of course, this is complicated result. What we get from it is that if we have some element from D2 minus something, which is positive, then we can represent it by some measure on this Wiener space of continuous function from Z1 to R. Okay. We apply this theorem to our self-intersection local time, and what we get is the form. Okay? So this limit here, of course, we clearly see that this integral of p epsilon d from something is clearly positive and the value. Okay? And so its limit, even though the limit is generalized on the variable, but it can be so seen that it is positive. Okay? So we have a positive generalized Wiener function. Applying this previous theorem, we can represent it by a unique, finite, positive measure on this Wiener space. So now, what is our conclusion? That in dimension greater or equal to 4, this non-existent double self-intersection local time can be considered as a generalized random variable, that is something that belongs to some space which is greater or bigger than the usual L2 space, and this generalized random variable is associated to some measure on the Wiener space. Okay, it's associated to some measure in the Wiener space. Okay. So now we will be concentrated on this measure. We have a measure on the big space of continuous function from 0, 1 to Rg, and we want to study its properties. Okay? Okay. Now first we derive the following formula. It tells us, now always keep in mind that we have theta u is a measure on this space of continuous function from 0, 1 to R. Okay? Now, how to integrate a function with respect to this measure? Here is a question. This is a complicated measure, belongs to some complicated space, but okay, it's a measure on some space. How to integrate with respect to it? So we find the following formula, okay? If you take any function from, of course, satisfying something, it belongs to G2 plus infinity, okay? Defined on this classical Hilbert space, then the integral with respect to theta u is given by the following integral here over delta 2. And here we have pt minus s d, it is common to use it, and we have some new function phi st from u. Okay, how is defined this function? This is simply the conditional expectation of this eta with respect to bt minus bs equal to. So if you want to integrate some nice function defined on the Wiener space, and you want to integrate it with respect to theta u, you need first to calculate this conditional expectation here. You will find the function that depends on mu, and you just need to integrate it with respect to bt minus s over delta 2. Okay. This expression will be useful in many results later. Okay. And maybe first application of this formula is to derive the measure of the whole space. It is not a probability measure, by the way, it's just a finite positive measure. So, but we can derive the measure of the whole space. It is given by this integral, and we even know that some asymptotics for this integral. Okay. Tell me, you ask me how did you find this? Of course, just if you go back one slide. So if I want to get theta u of the whole space, we just need to take eta to be equal to 1, of course. And if you take eta equal to 1, of course, here you will find this conditional expectation is equal to 1, and you get the integral over delta 2 of this Gaussian test. For these asymptotics here, a constant that depends on d divided by the norm of u to the power d minus 2, it is obtained from the asymptotics, the general result that we found before, this one. You remember the first estimate, this one. Okay? So if you take here alpha equal to 0, then alpha equal to 0, you will find exactly, we are in this case, because we have the d delta equal to 4, so we just replace alpha by 0 and you will find that some constant divided by the norm of u to the power d minus 2. Okay. And from here we can also think a little bit. So when u tends to 0, the measure of the whole space, of course, it's clear that it tends to plus infinity. Constant divided by the norm of u to the power d minus 2. So we have something also, again, that blows up around the origin. And this reminds us of the behavior in two-dimensional and three-dimensional cases. A similar property is also true for higher dimension, but in terms of associated measure. Okay. The next result is the support of this measure theta u. Okay, so where is supported this measure theta u? Okay, so the support is included in the following set of all the trajectories from the Wiener space, such that we can find an s smaller than t, such that phi t minus phi s is equal to u. Next, we will look to the moments of theta u, and then we will move also to some other properties of this measure. Okay, so we will need the following result. If a generalized function is positive and we consider its corresponding measure, like exactly we did with the generalized local time of self-intersection, then there exists a positive alpha such that this integral converges. This is called the Fernig-type theorem. And maybe we should say something about this theorem. Okay. There is a more general result about Fernig theorem. Okay. Fernig theorem says that whenever you have a Gaussian measure, okay, then if mu is a Gaussian measure, on some even a Banach space, but okay, even it can first begin by an Euclidean space, Banach space, okay, Banach space. Then you can find.
We need a measurement.
What?
For measure, we need a measurement.
You can.
For Borel, yeah? Banach space with Borel analogy.
Of course. Yeah. Yeah. Banach equipped with the structure of the Banach space. Yeah. So if we have a measure, then we can find the constant alpha. Okay, such that the integral exponent alpha log of x squared mu dx is finite. Okay. A positive one. Okay. So this is a function that is supposed to blow up when x tends to plus infinity, when the norm of x tends to plus infinity. But still, this function is integrable with respect to any result with this form of formulation is called the Fernig-type theorem. Okay. And here we have this theorem is a Fernig-type theorem for this kind of measures. Okay. By the way, it is maybe good to check this theorem and how to obtain this alpha if this is Rd. Okay. Yes, it will depend on the covariance matrix, and for example, it can be the I think minimum eigenvalue of the covariance matrix. Okay. Okay, but the result is even more general. Even in some Banach space, infinite dimensional Banach space is still here. Okay. And as a consequence from this kind of theorem, we deduce from here that if you consider moments for this measure, I mean, if you integrate, this is always finite. Right? If you have this exponential function is integrated, then these are integrated, because these can be dominated by exponential function. Or you can expand this as a series of alpha n r mod x or 2n divided, and each term will be finite. Okay. As a consequence of Fernig-type theorem, we deduce that this measure has finite points. The same thing here. Okay. We have a Fernig-type theorem for each measure of this kind, so it has finite moments of any order. In particular, our measure theta u associated to the self-intersection, generalized self-intersection. Okay. Maybe later I will need to define this probability measure. Theta u is just finite measure, but if we divide by the measure of the whole space, then of course we will get the probability measure on the linear space. Okay. Okay. So yes, our aim. So now we have a measure on a linear space, and we already have another measure, which is always defined. This is the linear measure. Okay. So we have two known measures now on the linear space, and we will try to see some distance. Okay. There is a quadratic Wasserstein distance that can be used to as a distance between probability measures. Okay. What is the quadratic Wasserstein distance? We consider any metric space, like we worked with its Borel sigma field, and we consider two probability measures which have finite second moment in the following sense. Of course, here it is even a Banach space, the linear space of continuous function from 0, 1 to RD. So we don't need really a distance. We even have an order. We have a finite second moment in the following sense. So the quadratic Wasserstein distance between the two probability measures is defined as follows, which is the infimum over all measures mu, which are defined on the product space, m times n. Okay? So we consider all measures on the product space, but with marginals equal to mu1, mu2. No mu. Marginals. So in U, the measure on m times n, we want its marginal to be mu1, mu2, which means that mu of A times m is always equal to mu1 of A for any Borel subset. Okay? And the mu of m times b, for example, will be mu2 of it for any A for any b. So these are the marginals of this measure. Okay. So we look to all these measures on the product space with marginals mu1, mu2. There are many of them, of course. And we try to minimize this integral here with rho 2xy over all these, over m times m, and minimize over all these possible measures with these marginals. Okay. This is the quadratic Wasserstein distance. And we need the following also: a definition of relative entropy between two probability measures on the same space. It is defined by the following formula. So it is an integral over m here of x, logarithm of d nu1 over d nu2 means the density of a nu1 with respect to nu2. and we integrate with respect to v mu1. Of course, if mu1 has a density with respect to v, otherwise the relative entropy is supposed to be n. Okay, this is the definition. Of course, relative entropy has maybe basic application in other fields than mathematics, but this is a mathematical expression. And by the way, if we have Gaussian probability measures, for example in RD, there is a very nice formula for the relative entropy. So we can find explicit formula for Gaussian measures. Okay, so now I introduced relative entropy, I introduced Wasserstein distance, and we will have some inequality that we'll use to derive some distance between, estimate the distance between this mu measure mu and the Wiener measure. Okay, so here is the inequality. So if we have two probability measures on Rn now, and suppose that one mu2 has a density with respect to the big measure, and that this density can be written as exponent of minus some function g of x, and with this function being positive and infinitely differentiable. Okay. And suppose that, in fact, any density that does not take the value 0 can be written as exponent of something. It is strictly positive. But just we need this v to be infinitely differentiable. Now suppose that there exists a constant kappa, that the SCN matrix of v is greater or equal than kappa times the identity. Now, SCN matrix is the matrix that contains, of course, v is from Rn, it is a function of many separate variables. Its SCN contains all the second order derivatives. Okay. SCN of v contains second order derivatives. It is a symmetric matrix, and we suppose that it is greater or equal than kappa identity. Again, maybe I think that I have spoken a little bit about this order between symmetric matrices, right? So greater or equal means that the difference, which is again symmetric matrix, should have positive eigenvalues. Okay? So write that A for symmetric matrices A and B, A is greater than B means that A minus B has positive eigenvalues. Okay? Right? Symmetric, positive, semi-definite.
I have a question. So the Wasserstein distance is symmetric something between mu1 and mu2, yeah?
Yes. Yes.
And on the right hand side we have entropy, which is not symmetric.
No, it is not symmetric. It is mu1 with respect to mu2. Yes. Yeah.
So can we have the same statement with another entropy? So
it depends on
no,
the
it depends on the form of mu2. Yeah.
Yes.
Mu2 is
Yes. Yeah. So here is the inequality. So the quadratic Wasserstein distance is less or equal than 2 divided by this constant kappa times the relative entropy. Okay. Now we will try, but of course this result here is stated for measures on Rn. Okay. But we have measures on infinite dimensional space. We have measures on the Wiener space. So the idea is to apply this not for theta u and the Wiener measure, but for the finite dimensional marginals. Okay, let's try to get this. So here is the aim. We want to estimate the quadratic Wasserstein distance between the finite dimensional marginals theta u tilde probability measure and the finite dimensional marginals of the Wiener measure.
A question. So one slide before, there was this Talagram inequality. What is it?
This is the Talagram inequality, yeah.
So let me go.
Yeah.
Let me.
Yeah, yes. So important inequality. Okay. Okay. Now,
Theorem of Blower, but inequality of
yes, the original result was stated by Blower, and okay, it is called Talagram inequality.
as
I
always.
don't know for what reason. Okay. Maybe Talagram was the first to just detect this inequality, but the proof was maybe done by Blower. Okay, now finite dimensional marginals of the Wiener measure. Okay, we denote by mu n the probability measure on Rd times n of B is always the Brownian motion. So here finite dimensional marginals, what we intend to say, the Wiener measure is like the probability measure of the Wiener the Brownian motion itself. Okay, as a whole process, what its probability measure is given by mu, and the marginals we will intend by the marginals is the following, the probability measures of the following vectors. Okay, so maybe. So mu. So this is a probability measure of b of 1 over n, so on b of 2 over n. This is a huge vector, okay? Because this is d-dimensional, and so on, until b of 1, bn minus 1 divided by n, and then b belongs to r d to the power. Now, if you make n greater and greater, these finite dimensional probability measures will, when n, what will it find? It will find mu, the probability measure of the whole unit process. Okay? It is a probability measure of the whole Brownian motion. Okay? Just to imagine, these are, you just take a finite number, then you make n bigger and bigger. Of course, the measures that you have become closer and closer of this, the measure of the whole process. Okay, but this is a finite dimensional Gaussian vector. This one, okay, and we can derive exactly what is the density of this Gaussian vector. Okay, so the density is exactly given by the following formula. Okay, so product from 1 to n, p 1 over n is usual Gaussian density that we use, xj minus xj minus 1. Okay. Now we want to do the same thing, but for this measure, theta u. Okay. For the measure theta u. What are the finite dimensional marginals? Trying to obtain them. Okay. Again, theta u is obtained from some generalized function. Okay. To define its marginals, we again will come back to a little bit to generalized function. So, if we define the following, of course, formula, f of b of 1 over n until b of n, take any function which is bounded and infinitely differentiable in Rd to the power n, and make this dual pairing with our generalized function. So what we obtain is like a pairing between f and some generalized function that we denote by rho 2 n of u. Okay. And this is a way to define some, from rho 2, we define some other generalized function, but it is defined on Rd to the power n. And this generalized function is exactly the one that will give us this, the finite dimensional marginals of theta u. Okay. Okay, we denote then by theta u n the associated measure in Rd to the power n. And okay, we can check that theta u n, so it is the associated measure. Okay, that the measure of the whole Rd to the power n is exactly MUD that I defined before. Okay, MUD is integral over delta 2 E K minus S U E, which is the theta u of the whole linear space. So theta u of the whole linear space is exactly equal to theta u n of Rd to the power n. Okay. Now we have the two finite dimensional measures, okay, from the Wiener measure and also from this theta u, the measure theta u that is associated to the generalized self-intersection. And we will try to compare them using this Wasserstein distance and this Laurent inequality. Okay. So first of all, maybe we did the following lemma that tells us how to compute this conditional expectation of P epsilon d Wt minus Ws minus u with respect to Wt1, Wt. Okay, it is a technical lemma needed for the following result, but again, it's a good exercise to prove this. Of course, here W is a d-dimensional Brownian motion, okay, and how to compute this conditional expectation. It was a nice result, and what we find is the epsilon, another Gaussian density with parameter epsilon plus sigma square. Okay, sigma square is defined here, and inside we will find the following increments from the Brownian motion. Okay. It is needed to, this result is needed to define the density of theta un with respect to mu n. Okay? If you remember, this density is needed in the Laurent inequality. Okay. Now, the measure theta un has a density with respect to mu n, okay, given by the following expression. Okay? So why we look for the density of theta un with respect to mu n? Because we have the relative entropy and we need this relative, this density of one of the measures with respect to the other. Okay? It is needed in the relative ontropy. And we were able to exactly obtain this density explicitly. It has the following formula. Okay? With some parameters, some. Okay. Here, alpha j is given by this, the big measure of the intersection of these two intervals. The distance here, square, it is the distance in the L2 sense of this function here, and the linear span of the distance between a vector and some subspace, linear subspace. Okay. Okay, now, okay, we have a part from the inequality which is ready, since we have the density of theta un with respect to un, so the relative entropy is almost has an expression. What remains is the, if you remember, just here, yes. So we almost have this relative entropy. Now remains to find this kappa. Okay, so look to the density of of our measure theta un with respect to mu n, and try to find this constant kappa here. Okay. So, okay. Now, the measure mu n, I recall it is the measure of this vector. Okay, and it has its density. Okay. I recall the density here. It is written exactly. Here it is. Okay. So this density is a product of this Gaussian density here, so it can be written exponent of minus something. Okay. And we need to compute the Hessian of that something and find constant times the identity such that the Hessian is greater or equal than. Okay? So we computed everything and it was nice work. The Hessian matrix of V has eigenvalues explicitly given by this expression. Okay. In particular, the best constant kappa n such that the Hessian is greater or equal than kappa n times the identity matrix is given by the minimum eigenvalue, and it is given here. Okay. Okay. Let's see the proof, how it was done. It's a good exercise of the matrix, some linear algebra. Okay, so we recall that the density of mu n is given by this product, and we can derive easily the. So this product can be written exponent minus something. Okay, and we can derive the Hessian of that expression. Okay, and the Hessian is given. Matrix of V is the following matrix. It is a three-diagonal matrix. Okay, it is a constant matrix. It doesn't depend on x1, xn. Okay, and so the task was to find the eigenvalues for this matrix. So it can be written first as a tensor product, because you see here that there is an identity in all the entries of the matrix. So we can write it as a tensor product of this matrix here without this identity, and product with a tensor product with the identity. So it is enough, in fact, to find the eigenvalues for this A. Because the eigenvalues of a tensor product will be products of eigenvalues. Okay. And now, exactly. This matrix here can be written in the form in relation with a more simple matrix B, and here we can find the eigenvalues for this matrix B by just solving a linear system. Okay, by solving a linear system, we find exactly the eigenvalues of B, and finally we can deduce the eigenvalues of our Hessian matrix and take the smallest one. Okay, so it was really good exercise. So now, combining all these densities and eigenvalues that we obtained, now we can state the Talagrand inequality for the theta un and un. Okay, and we have the first we have the relative entropy. Okay, just take the relative entropy. We can have an upper bound for it given by the following expression. I represent MUD is this integral here, and another term here, logarithm of sigma square. Okay. Sigma square is defined before. It is the density between indicator ST and the linear span of many indicators of 0, 1 over n, and so on.
So there is a subtraction. So minus,
yes.
minus log, minus.
Yes.
Minus
okay. Of course, this is when u tends to 0. This yes. This is like a constant. This one here, it is like a constant. But this one is supposed to this logarithm of sigma square. Sigma square, if you just go back to see sigma square, understand what's going to happen. Okay, sigma square. Okay, it is given here as the distance, square distance between the indicator of ST and the linear span of this indicator. Of course, when n tends to plus infinity, these indicators become more and more like dense in the L2 space of the 1, and of course this distance will tend to 0. Okay, so this sigma square is supposed to tend to 0. Okay, now I go back. So its logarithm, of course, is supposed to tend to plus infinity, to minus infinity, and with this minus here, this is intended to go to plus infinity when n tends to plus infinity. Okay. Finally, so we have the estimate for quadratic Wasserstein distance between theta u and theta and mu n. Okay, it satisfies the following inequality. Just combining the previous result. This is 2 divided by kappa n, remember, and this is an estimate for the relative entropy. Okay. Of course, we can check that all this upper bound is going to plus infinity when n tends to plus infinity. Maybe this seems not to be a good thing, but one should take into account that when n tends to plus infinity, of course, these two measures, one will tend to theta u, the measure theta u, and the other will tend to mu. Okay, so the limit will be like partial time distance between the measure theta u and the measure the Wiener measure. But these two measures, if you take, generally, if you take two measures in an infinite dimensional space, they tend more to be singular, more than to be, one is absolutely continuous with respect to the other. So here, when we have this limit of relative entropy to be infinite, it's quite predictable because we do not predict that theta u is absolutely continuous with respect to the dimension. Okay? They both live in an infinite dimensional space, and they do not have the sense to be one is absolutely continuous with the other. So maybe this estimate is good for fixed n, but no need to take n to infinity because it will be meaningless. Okay.
So, how we are going to use this? So, estimate of the distance measures?
Estimate of the distance is just to trying to compare theta u and mu, okay? Because now we have mu in the linear space, and we already have mu in the linear measure, so we're just trying to compare them in some sense. Okay?
Okay, but just having the comparison of
compute the distance
some
between.
particular
Yes.
first M stuff.
Yes, for a finite
Does it
dimensional
give
margins.
some information about this stuff intersection?
Not, I don't think so. This is a little bit far.
We cannot conclude this.
Yeah, I don't say this, but it doesn't seem to be really. One can derive a conclusion about self-intersection from here. Okay. We already know we are in the situation where the self-intersection equal time does not exist as a usual random value, so we are already working with it as a generalized function.
Yes.
And so we are defining a measure that represent this self-intersection equal time, and we're trying to make some estimates related to this measure. So,
Interesting to say. If they are very close to each other,
yes.
all these finite dimensional margins, so to say. Can we say that then there are no intersections or more intersections or less intersections or
Okay.
can we compare
Okay.
something else based on this?
It's a good question. Okay. But according to the self-intersection, without local time, just the self-intersection, we are in dimension greater or equal than 1/4.
Yes.
So already know that there are no self-intersections.
Okay.
So we are trying to construct something that does not exist.
And it is still quite close to the Wiener measure.
Yes. Yes, it is somehow close to the Wiener measure for finite dimensional. Even in finite dimensional marginals, we can even find the density, you know? So what we found is that even theta u n,
Yes.
we have this.
Yes.
Even we have this. But when you go to theta u and mu, they are supposed to be singular. Okay? So
But maybe it makes some other sense. There are no intersections, but probably this is a kind of a measure of some positions of the polymer where they are this, you know.
yes, it can be.
Close to positions.
Yes, it can be. It can be.
So probably there are some
Yeah.
further interpretations.
Yes, it can be. Or it should be. One has to think about it.
Yeah, think
This
what
is a
you
good
measure.
question,
Think
no?
what you measure. So
Yes.
probably there is something what you measure.
Yes. And why not? One should concentrate a little bit on this. That's a good question. You know, sometimes you have, after working on something, you don't have to leave it and go to something else. Maybe
Yes,
you
yes, you have to
think
switch on.
Yes, you have to think again about it. You
Yes.
have to understand it again and again. Maybe
From
there
some
is,
point to another point of view.
yes, it may have some other explanation, some other
Yes, yes. Probably
significance.
there is some physical object, so to say, which fits to.
Yes. Good task for me. Good task for me. It only remains to say thank you for your patience.
Other questions or comments? Yes, this last questions, they were quite technical and maybe a little bit difficult for you, but at least you can understand what modern mathematics do. So I hope you get some new experience and maybe a little bit knowledge you get in this field, and you're welcome to ask questions. Maybe you can write to us, or at least you can read once more what we discussed now, and maybe you will find something interesting and you can continue your work in this direction. So
You may write your PhD on this subject.
yes, you can choose. You see, there are a lot of questions that haven't solved yet. So you can find a lot of questions that you can try to solve by yourself, and this will be your master thesis, or even PhD thesis. So maybe that's thanks to our lectures once more. So thank you.
Can you write your email address on the
Yes,
top?
okay.
Maybe
Yeah.
sure.
We all,
Yes.
we all can
You all. Maybe